is David Van Vranken. This is our 7th lecture here in the Chemistry 51C Organic Chemistry course here at UC Irvine. And I wanted to stop and reflect for a little bit on this place that we have arrived at in history, where the coronavirus pandemic is raging. People are hunkered down, wearing masks. Just seems like everything is shut down. People are being laid off left and right and losing jobs. It just seems to be so much hatred and factionalism going on. People finding reasons not to get along. And it's easy to feel like that we're living in a time that is totally without precedent. So I wanted to stop and go back 100 years just to remind yourself what things looked like 100 years ago. Because 100 years ago, in 1918, there was another pandemic that was raging. And the world was trying to kill itself. That was right during World War I. People were still waiting in lines to get masks. And so let's go ahead and take a look at what it was like to be a student in college 100 years ago. This is the University of California. There was only one campus at the time. That was the Berkeley campus. And here they moved a barbershop outdoors so that they could follow the distancing guidelines with rules. You can see that people are wearing masks. They found a way to make it work. They just moved the barbershop chairs outdoors and gave people haircuts, and found a way to keep things going somehow. These are students at the normal school in San Jose. It's the San Jose campus of the normal school. And of course, everybody's wearing masks at that time. The normal school turned into the Cal State University system. And they also had a Los Angeles campus. The year after this photograph was taken, the Los Angeles campus of the normal school was taken over by UC in order to become UCLA. The same thing was going on at Stanford University, right near San Jose, right near the normal school. Here's a quote by Mary Sloan Wilbur from that time, who was a student at Stanford University. She says, "When I first came to Stanford in the fall of 1918, most of the men were in the Army, and the fraternities were closed. A number of the houses opened up to be used as infirmaries. It was mandatory that everyone should wear flu masks. You were fined if you were found without one. They were bought for 10 or 15 cents apiece and were made of cheesecloth with loops over the ears." And one of her peers noted, "Professors even lectured through the masks as their students, similarly attired, struggled to make sense of the muffled sounds emanating from the front of the room. They didn't have the option of anything like remote lectures or Zoom or recorded lectures. And so in a way, we're fortunate that at least you don't have to listen to me giving my lectures through some kind of a mask." You know, it's easy to get caught up in the situation and feel like, well, I'll wait until the pandemic is over. I think maybe some people are starting to see a future where there's not a pandemic raging and stopping us from doing everything. But, you know, there were loads of people who went through college back 100 years ago and managed to do great things. And maybe they didn't know what they were headed for at the time, but they kept going. Edith Head was an iconic designer for decades, won an Academy Award for fashion design in the movie industry. Stephen Vincent Benet was a Pulitzer Prize winner for poetry and for short stories. Thornton Wilder, an author and a playwright. If you've ever heard of the molten core model of the Earth, where the Earth has this molten iron core, that's Inga Lehman's work. She was in the class, she was a student during the flu pandemic in 1918. Pearl Young was a student at the University of North Dakota, where hundreds of students died of the flu on her campus during that year. And she went on to earn a degree in mathematics, in physics, and in chemistry at the same time, and went on to become the first woman scientist to be employed by NASA before it was even called NASA. Arnold Beckman, you may have heard of him because there's a Beckman Center here at UC Irvine. There's a high school. He's a Southern California local. And he went on to develop the first commercial pH meter and other scientific instrumentation, and became well seen for that. Linus Pauling is really an iconic chemist from that time. Won 2 Nobel Prizes. So if you're familiar with the electronegativity scale, that's Linus Pauling. Alpha helices and beta sheets from protein structure, that's all Linus Pauling. These people kept going. They did not let the flu pandemic or any sort of a pandemic stop them. And I'm just going to encourage you to keep that mindset that there's something beyond the coronavirus, and just keep going, because the future is going to take you in great places. Let's come back to where we left off in our lecture. We were talking about hydrido reagents that transfer hydrido groups to carbonyls. So it's so great to be talking about additions to carbonyls. And so let's continue talking about some of the chemistry of lithium aluminum hydride, also called lithium tetrahydridoaluminate. So when you have carbonyl compounds like carboxylic acids or esters, they get reduced. So we've already talked about reduction of esters by lithium aluminum hydride, but let's go ahead and talk about the reduction of carboxylic acids, because it's the same idea. If you have either an ester or a carboxylic acid, I'll go ahead and draw out a carboxylic acid, the same conditions that you use for reduction of esters also reduce carboxylic acid. So it's step 1. So remember, you have to enumerate these reagents. Lithium aluminum hydride. Step 2, water. That's a workup. We're not trying to do SN2 or anything. We're just trying to protonate the anionic species to make neutral products. And when you do that, what you get out of this reaction is you get water is the other byproduct. There's 2 oxygens. One of them stays attached. And we've ended up reducing the carbonyl down to a CH2 group on this functional group. So we can do a similar reaction using amides. And this reaction, I promise you, is going to come back 5 chapters from now when we start talking about the chemistry of amines and how to synthesize amines efficiently. So if you take an amide that has 2 alkyl groups on the nitrogen, 1 alkyl group on the nitrogen, no alkyl groups on the nitrogen, you can use lithium aluminum hydride to reduce down the carbonyl group and keep the carbon-nitrogen bond, so it's distinctive from an ester or a carboxylic acid in a way. So it's the same reagents, lithium aluminum hydride, not sodium borohydride. That wouldn't react with any of these ester or carboxylic acid derivatives. And then a water workup. So that 2-step procedure. And when you do that, you end up with something that looks like this. We've lost the carbonyl group in both of these cases. So we usually don't write out the H atoms that just got added there. So if I ask you what happened, I hope you don't say that you removed the carbonyl group. That's superficial for you to say that. What you should say is you added 2 hydrido groups that we don't draw. So to be able to see the things that we don't draw, that's super important for this quarter. Let's go ahead and look at the mechanism for reduction of an amide by lithium aluminum hydride. It's kind of a long drawn-out mechanism here, so I'm going to divide it into 2 different slides as I write this out. And I'm going to draw the mechanism for reduction of an N-alkyl amide where there's 1 R group on the nitrogen. I'll draw the H sticking over here because the first step when you treat this with lithium aluminum hydride, a hydridoaluminate reagent, is that it's going to remove that proton from the nitrogen. And so give me just a second here to okay, so the first step is that we're going to do nothing more than an acid-base reaction. If you put lithium aluminum hydride in water, it's going to immediately deprotonate the water. So I'm going to show taking this proton off. But just to make things a little more helpful for the mechanism, I'm going to kick the electrons all the way over here to the carbonyl group. That's why this amide NH is so acidic. Not quite as acidic as water, but just about the same. So it's very easy for lithium aluminum hydride to deprotonate that. It's such a basic and nucleophilic reagent, very basic. And so we're going to generate this species here that can now have they can now be reduced. But first, we're going to coordinate this with something. There's two different ways to draw this mechanism. I would normally draw this O- coordinating to the lithium. There's a lithium cation floating around. The book shows it coordinating to the aluminate, just to honor the fact that aluminum loves oxygen. Oh my gosh, it's so awesome to form a bond between oxygen and aluminum. So let's go ahead and draw it like that, the way the book does, to follow through with that. Whoops, I think I erased that on accident. Let me see what I can do to redraw that, to redraw my aluminum species here. So there's my aluminum. Let me draw that lone pair right there, ready to attack the aluminum. And so now we've got this species, so it doesn't have the negative charge on the oxygen anymore. And I have to remember to draw that negative charge on the aluminum. That's now an aluminate with a negative charge. But the important part is now that there's not a negative charge on the oxygen, we can add another hydrido group into this by having this react with another equivalent of lithium aluminum hydride. There it is. And now I'll go ahead and draw that bond adding into there. And so now we've added the first hydrogen carbon bond to this in this mechanism. And so we're going to have an N- down here. And that oxygen is still attached to the aluminum. This mechanism is going to seem really uncomfortable to you because the book doesn't, and we haven't been drawing out the fact that there's a lithium cation floating around. In fact, it's coordinated to the oxygen, but the book doesn't ask you to draw that, and so I'm not going to ask you to draw that either. So we've got this carbon-hydrogen bond that we've just made, and we've got a lone pair on an N-. Boy, that N- lone pair is more basic and more nucleophilic than an oxygen minus lone pair. So let's go ahead and use that lone pair on that N-, on that amido anion, to push out this as a leaving group. So again, I expect that step to kind of freak you out. I expect it to be uncomfortable because you're going to be saying, wait a second, does that mean that we're going to generate a species that has two O- right next to each other? Well, according to our arrow pushing, yes, but in fact, the lithium plus is coordinated to the oxygen before it leaves. But because the book doesn't show that, I'm not going to show that either. But in case you're getting freaked out, if you wanted, you could first coordinate it to lithium to look like a more realistic mechanism. But here's where we're at in the mechanism. We've generated a species that we're going to see very heavily in the next chapter, and this species is called an imine. Let me just go ahead and write that name there. This is an imine. So step one is of the lithium aluminum hydride reduction of an amide is to form an imine intermediate. And let's go ahead and use that imine intermediate. We're going to go a little bit further here with this mechanism. I'm going to take that imine, and we're going to add another equivalent of the tetrahydrido aluminate. There we go. Let's make another carbon-hydrogen bond. And here's our tetrahydrido aluminate reagent with those super nucleophilic, long. Whenever I see that negative charge on aluminum, all the bonds to aluminum are nucleophilic. I'll push the electrons up. So we're going to see more of these types of additions to imines in the next chapter. And so when we do this, now we've added both of the hydrogens to that amide. Now, let me explicitly draw the two hydrogens that are there now. So there was already a hydrogen from the first addition of a hydrido, and now we've just added a second one, and we've regenerated an amido anion. And that's just going to sit there. It'll sit there as we go to lunch. We can come back the next day. It'll sit there until we work this up with water. That's way more basic than water or alcohols. So if we put some water in here, especially if we dump a bunch of water in there, it's simply going to pick up a proton from water. You couldn't stop that from happening. So now we're in the workup stage, step two. Step two, remember, was just to dump some water in there and just try to convert this into a neutral compound that we could then extract into an organic solvent and then evaporate the solvent. That's usually the goal in organic chemistry, is to make neutral compounds that we can extract into organic solvents and then evaporate the solvent. So again, whatever you have an amide carbonyl, you can reduce that carbonyl down. Let me take an example that might freak you out a little bit. I'll draw a cyclic amide. Cyclic amides are called lactams. And let me try to spruce this up a little bit. I'll put two methyl groups there to try to make it exciting. Here, let me try to make it really weird looking. I'll put a spirocyclic cyclobutane ring on there. But when you treat this with that same set of conditions, lithium aluminum hydride, step 2, water, it's going to reduce the carbonyl down. Right? With an ester, you cleave the carbon-oxygen bond of the ester, but with an amide, you keep the carbon-nitrogen bond. So the product of this reaction would be that we would keep the carbon-nitrogen bond that was there in the beginning, and we would simply reduce down the carbonyl. This would be the product for the reaction. Remember, for heteroatoms like nitrogen or oxygen, you always draw the H's. There's never such a thing as, oh, we just assume you know how many H's are attached. That's one of the drawing requirements. For carbon, you're not required to draw all the H's that are attached to carbon. Okay, so you need to know this. I promise you, this is going to be a major theme for synthesis 5 chapters from now when we start talking about amines. Okay, big time shift here. Let me just take a break here. All right. We just finished talking about lithium aluminum hydride and sodium borohydride as hydrido transfer reagents. And sodium borohydride is really good for ketones and aldehydes, whereas lithium aluminum hydride, man, if your mama had a carbonyl group on her, I would reduce that carbonyl group. It goes after every carbonyl group. Lithium aluminum hydride is so reactive. Now, what I want to do is I want to take a look here at the periodic table and think about the impact of electronegativity. If you make a bond, right, let's come over here and I'll try to highlight carbon because that's really the centerpiece of organic chemistry. If you make a bond between carbon and a more electronegative atom, our expectation is that this bond is not in any way ever going to be nucleophilic. Let's just write that down because that's not ever a nucleophilic bond. Let me see, not nucleophilic at all, ever. There is no time that you would ever use that bond to attack something. Maybe lone pairs on an atom, but not that bond. But the opposite thing occurs if we bond carbon to things over here on the other side of the periodic table. If we make bonds from carbon to things on the left side of the periodic table, lithium, sodium, magnesium, those bonds are amazing, crazy nucleophiles. My gosh, it's just insane how much of a change you get there. So let's go ahead and depict that. So if I have a lithium carbon bond, man, that is one of our best nucleophiles, most powerful nucleophiles. Let me write way here. Way nucleophilic. Way. See, it's not enough for me to say, I'm not going to just say way. Let me say way nucleophilic and basic. Wow, that carbon-lithium bond, man, that's amazingly nucleophilic and powerful. Powerful than any other nucleophile you have ever seen or will ever see in the Chemistry 51C series. It's a similar thing if you have sodium. We have it's not as easy to handle carbon-sodium compounds that have carbon-sodium bonds, but you have already seen one. And that's sodium acetylides. You learned that you could make sodium acetylides way back in chapter 11 in the alkynes chapter. You use sodium amide to deprotonate, you make those bonds. Those bonds are way nucleophilic. They're way nucleophilic. And similarly, over here with magnesium, that's the other common, alkaline earth metal that you can bond to carbon. And when you do that, and it doesn't matter what the R could be phenyl, right? I'm not saying what the carbon-lithium thing could be phenyl, could be alkyl, ethyl, butyl, isobutyl. Most of those they sell. So we have to have a second bond to magnesium. Usually it's a halogen. Almost always it's a halogen. That bond is nucleophilic. And we're also going to see similar reagents with bromomagnesium. It's all the same idea. There's no substantial difference between a magnesium carbon bond when it's chlorine or bromine on the magnesium. And then also iodine, you'll also see attached to the magnesium. The bottom line is it's a carbon-magnesium bond. Wow. Those bonds, let me highlight them. I love them so much. Now, what color should I use? I don't know what color this is, chartreuse or something. Oh, yeah. Look at those bonds. Man, those bonds are super, Super, I'll write super duper, otherwise you won't get it. Super duper reactive. The trick here, I think the trick, is that it's super duper, they're both basic and nucleophilic. Basic means it wants to attack protons. That's not always what you want. What you really want is to form bonds to carbon. That's nucleophilic. So we got to watch out for that basicity, but it's that nucleophilicity that we want to capture. We have a name for these carbon-magnesium compounds. They're pretty, they're kind of their own class. We refer to these here, the carbon-magnesium compounds, as Grignard reagents. Grignard won the Nobel Prize. I forgot the guy's first name. Grignard won the Nobel Prize for developing those around 1900, way more than 100 years ago. Okay, let's take a closer look here at these reagents. Boy, we're finally getting to the great stuff in organic chemistry. So how do we think about the character of this bond? Right, we're going to draw, I will tell you that you should draw these reagents, whether you have carbon-lithium bonds or carbon-magnesium bonds, with a covalent bond there. But if we try to satisfy electronegativity, right, carbon is more electronegative than lithium. And this is kind of weird thinking. It should be weird thinking for you. It's like, wait a second, I thought every heteroatom was always more electronegative than carbon. Not atoms from the left side of the periodic table. So oftentimes what you'll find is that in older textbooks, they would draw these types of species in their other resonance form as these charge separated species. But in fact, there's a covalent bond there. Sometimes it will help you every once in a while to draw this resonance structure just to remind you that the carbon is the nucleophile. You might have this sense that, gee, I thought all nucleophiles had to have a lone pair that they attack with. No, that's not right. Right? You should be just as comfortable using this covalent bond over here between carbon and lithium to attack things. That's what we're going to really do in this chapter. It's anything that you think that you can do with that lone pair, like attack a carbonyl, you could also do with the covalent carbon-lithium bond when you draw it in this covalent bondage structure like this. Watch how easy this is. See? I form a carbon-carbon bond by using the methyl lithium bond, and I take the electrons away from lithium, and I end up forming a bond. I end up forming a bond to the carbonyl carbon, and then the lithium would just be sitting here, just like that. You just you rip the electrons away from the lithium that didn't want the electrons in the first place, and you give them to the carbonyl carbon. You might think, well, it's easier for me to draw a lone pair and a minus and a plus. No, it isn't. It's not easier. It's more work to draw the lone pairs. So you would really have to get used to drawing bonds to things like lithium and magnesium and using them as nucleophiles. Really critical for this quarter that you become good at that. Now, where do we get these reagents from? So let's go ahead and talk about how you make these reagents. So you make these reagents from organic halides. The alkylithiums typically come from the chlorine, the organochlorine compounds. You get better yields with the organochlorines. You don't need to worry about that. If you wanted, you could claim you're going to make it from organobromine compound. So how do you convert an organochlorine compound like this to one like this? How do you convert chlorobutane to butyllithium? Well, in fact, they sell tanker carloads of butyllithium. It's one of the most common organolithium reagents. Nobody ever makes that. You buy it. They make it in a big industrial factory complex. The way you do is you add lithium wire. Most laboratories have these little bundles of lithium wire in mineral oil so it won't react with oxygen. And you just cut up some strips of little bits of lithium wire, and you throw them into your reaction, and it makes that bond. Now, let me be clear about the stoichiometry here. It's actually, if I want to keep track of the stoichiometry, it's 2 lithium atoms makes this plus lithium chloride. So you usually don't write the lithium chloride as the byproduct, so it's kind of in a way weird to say 2 lithium atoms there. If you chose not to do that, if you chose to leave out the number 2, drawing the equivalency of the lithium, I wouldn't count that as wrong. Okay, so how do you make a Grignard reagent with carbon-magnesium bonds? It's just as easy. It's just as easy to write out, and it's just as easy for you to memorize. So if I wanted to convert this carbon bromine bond into a super duper powerful nucleophile, you already know how to put bromine atoms on benzene rings. Maybe not at the meta position, that you don't know how to do, but if you have a bromine atom on a benzene ring or anywhere else, or at a benzylic position or at any other position, you can convert that into a nucleophile. Just like the lithium case, you add magnesium. It's that simple. And now you've changed what kind of looks a little bit like a leaving group. Um, it can't leave from the benzene ring. You've converted that into a super powerful nucleophilic bond. Just like that, you change the character of a carbon bromine bond, the bromine from a leaving group, and you change that bond into a powerful nucleophile. Now, it is true that these reactions always require some sort of an ether solvent, and I don't know why, but the book feels like it's super important for you to draw the solvent for forming Grignard reagents, to note that it's ether and to memorize that. Honestly, I don't care whether you memorize the fact that there's ether is required as a solvent for making Grignard reagents. Um, there's interesting details behind that, but we're not going to talk about it this quarter. So it's the same with chlorine compounds and iodine compounds. It's just you add magnesium metal. We have these jars with these little strips of magnesium metal that have been ground off of a block of magnesium, and you just mix that in, and it makes Grignard reagents. Now you already know how to make sodium acetylides. This should be, well, you probably forgot it, but there's this CH bond, and the proton on an alkynyl CH is much more acidic than a regular alkane. And in this case, we can use a base. It's a super powerful base called sodium amide. You weren't really prepared to hear about sodium amide as a base back in chapter 11, which is where this stuff comes from. We're going to talk more about these bases in a few chapters, these amide anion bases. But this is how you make sodium acetylides. I think in that chapter they drew it out as this charge separated resonance structure. But again, there's a covalent bond there, and that bond is nucleophilic. That carbon atom at the end of the acetylene, doesn't matter whether you draw a covalent bond or you draw it as C minus. Well, that carbon is nucleophilic and basic. Keep it away from water. And then you can use it as a nucleophile to attack things and make carbon-carbon bonds. Wow. Okay. I mentioned that these compounds, organolithium compounds, Grignard reagents with carbon-magnesium bonds, and even that sodium acetylide, they are super basic, and nucleophilic. So if you want to use them to attack carbonyl groups, which you do, and make carbon-carbon bonds, keep them away from water or anything that can protonate them. Here's what will happen instantly if you have a carbonyl, a juicy carbonyl group, but there's water or OH. Sorry, I'm trying to find my my black pen here. If you have some sort of amazing carbon-lithium compound, this is butyl-lithium, and you have a carbonyl group, but there's water or an alcohol present, faster than this will attack any carbonyl. If there's an OH compound within 1,000,000 miles, it's going to deprotonate the OH faster than anything else. And I promise you, you don't want to do that. That's just a huge waste. This carbon is going to take the electrons away from lithium and give the electrons to a proton. So the lithium will just end up as lithium plus. If you spent a lot of money buying this organolithium reagent or making it in the laboratory, the last thing in the world you want to do is stick a proton on there. Boy, that would be a huge waste of a reagent. And the other byproducts here would be the ethoxide anion. Boring, and then lithium plus, boring. So that's not what you want to do with organolithiums. You want to add them to carbonyls. And it's the same concern if you have a bond to magnesium, to a halomagnesium group. So if you have a bond to a bromomagnesium group, that bond is basic and nucleophilic. Keep it away from alcohols or water. Man, we have equipment in our lab, gas lines and all kinds of stuff to keep air. The air you're breathing right now has so much water vapor in it that it will kill your reagents. So we do everything we can in a modern organic chemistry laboratory to keep those reagents and your chemical reactions away from this crappy wet air that you're breathing. Let me take the electrons away from the magnesium, and I'll attach the phenyl bond to the proton instead. So that's what we're doing here. We're trying to show what happens if you're not careful about keeping your reactions rigorously dry. Well, you just wasted, right? If you went through the trouble of brominating a benzene ring and then converting it into this Grignard reagent, the last thing you want to do is stick a proton back on the benzene ring. Well, you just wasted a whole lot of time and effort and energy. And of course, that's the leftover stuff here would be completely uninteresting. That goes down the sink. It's just like salts that you can find in any water sample that you get around. So you would never want to have water or any OH groups present. So you're trying to watch out. You're trying not to do these types of reactions. Let me show you one other reaction that every instinct you have is going to make you want to do this. There's one thing that you can't do with these reagents. When I tell you that they're reactive, one thing that you cannot do with these reagents that you've spent 6 months trying to learn how to do is SN2. These reagents are no good for making bonds using SN2 reactions. Why is that? Well, because when you have alkyl groups, there's protons nearby. And these compounds, the basicity of these types of compounds is more important than the nucleophilicity for forming bonds to carbon. And so if you tried to do an SN2 using any of these types of compounds, you would simply get mostly E2 elimination. And so alkylithiums and Grignard reagents are great for adding to carbonyls. Don't use them for SN2. That's not what they're for. And you might be saying, well, why did I spend 6 months learning nothing but SN2? I don't know. I have no idea. So, boy, but we want to use these to add to carbonyls. So, yeah, so instead, I'll just write here. Instead, you get E2. Right here. Instead, you get E2. All right. So we've got this powerful set of bond-forming reactions. Let's go ahead and use it. Let's go ahead and take a look at how these things work. So let's go ahead and start off. I'm just going to sketch out some reactions here. Let me go ahead and take some carbonyl compounds. Oh, here's an aldehyde, benzaldehyde. And let's suppose I made some sodium acetylide, like I used to back in chapter 11, where we used sodium amide and reacted with terminal acetylenes to make, I didn't draw it here, but there's a nucleophilic carbon-sodium bond in there. And don't use those for SN2. Maybe that's all they told you about back in chapter 11. What we really use these for is we use them to add to carbonyls. So when you do this reaction initially, you'll generate a carbon-carbon bond and an O-. So we follow this up with an H2O workup because we want to extract the neutral, the protonated. We use the water to in fact, let me change the color of this. I'm going to change the color so you can see where the OH compound comes from. I think I erased a little bit too much. Let me use a different color here. I'll use a glorious green color here, and I'll just try to indicate that it's the that the H that's on the alcohol, and again, we need that to be neutral, came from the water workup. So initially there was an O- in there. We work it up with water, and now it's neutral, and we extract it into organic solvents, and then evaporate off the solvent. Now, you have to look out for formation of stereogenic centers. I've just created a product that has a stereogenic center here. This alcohol, this carbon atom that used to be the carbonyl, now has 4 bonds to it. And so I'm going to write plus E, but you can't do that with our sapling system that we use for our online homework system. In that case, you would have to draw out, literally explicitly draw the enantiomer to make it clear that that you know you're forming a mixture of 2 different stereoisomers. Okay, let's go ahead and take another carbonyl compound. It's so exciting to take carbonyl compounds and make, finally, after months and months of Chem 51, months and months of organic chemistry, it's so exciting to be able to make bonds by addition to carbonyls. Okay, what would be another? Let's use phenyllithium. Right, we can make phenyllithium. If you brominate a benzene ring, you can convert it to phenyllithium by adding lithium metal. And we're going to protonate the O- product. So I'll remember, notice how in every one of these cases, I'm working the reaction up by adding water in there. So when I add the phenyl group, I start off with an ethyl, and I start off with a methyl, and I add a phenyl group on there. Let me draw those three groups. But I'm going to draw a stereochemistry here for this product. So in this case, I'll draw the product where the phenyl group adds from the front face of the carbonyl, and we protonate this with our workup, so we don't want to get stuck with an O- compound. But we're also going to get the other enantiomer in this reaction where the phenyl group adds from the back side of the carbonyl. So we'll get the mirror image. Anytime you generate a new stereogenic center, we have no ways to control that we're going to teach you with these types of addition reactions. So see how easy it is to make carbon-carbon bonds. It's just this is how you make organic molecules bigger and more complex as you make carbon-carbon bonds. We can use cyclic substrates as well. Let's take cyclopentanone. And this time we'll add a Grignard reagent to this. I'll make ethyl magnesium bromide. There we go. We'll work this up with water, H2O, so we can protonate the O- product that we get. Now, because of symmetry, you don't get two enantiomers in this case because both the CH2s on both sides of that center are identical or non-distinguishable. So there's only one product, only one stereoisomer in this case that we form when we add that ethyl group in to the carbonyl. So it's super important to be able to make carbon-carbon bonds, and this is literally the most important carbon-carbon bond forming reaction that you will see in, from chapters 1 to 22 of the Gorzinski-Smith textbook for the most of the organic chemistry series. I promise you there will be questions where you are required to know how to use these reagents in every single conceivable circumstance. So practice using these reagents. They are super important for organic chemistry, for any organic chemistry course that anybody takes anywhere. So, organic chemists love to make carbon-carbon bonds and love to make bigger and bigger molecules. And so if you work as a medicinal chemist or a synthetic organic chemist, you're typically going to be confronted with targets that you want to make. So how would you make a molecule like this? And the idea here is that you want to be able to work backwards. If I tell you how to make this, I hope whenever you see an alcohol, you're thinking, well, I know how to make bond alcohols by adding things to carbonyl groups. There's three different groups attached to this center here this center right here is called a carbonyl center. We don't really use that term much. You don't really need to know that term. You just need to know that you could have made this by adding to a carbonyl. But there's three different approaches you could have taken, and I expect you to know all of them. So, for example, let's suppose we made this by adding some sort of phenyl nucleophile. So if we made this by adding phenyllithium or phenyl magnesium bromide, doesn't matter. I'll use phenyllithium. And then I think I've got a bottle of phenyllithium in our lab. That's supposed to be a lithium atom there. Follow that, right? We always show that second step. Enumerate the steps. If you don't enumerate the steps 1 and 2, that's wrong because the phenyllithium would just react with the water. So what would our ketone have to be if we were to make this by adding a phenyl group? Well, the ketone would have to be this. Don't worry about the stereochemistry here. You have no way to control the stereochemistry. I'm not sure whether, let me just write plus E to indicate that you're not really, right? Strategically, you would be simply asked to make the enantiomer. So you need to recognize how to work backwards. But there's also two other groups here. There's a methyl and the alkynyl group. And we could have made this just as easily by adding either of those two groups. So here's another way we could have made exactly the same compound. If we added the acetylide group, we would have started with a ketone that had a methyl group on it and a phenyl group. And we could have added step 1, sodium acetylide, NaC, triple bond. Whoops, that's supposed to be just a triple bond there. CH. Step 2, water workup. There we go. And we could have made that compound as well, using that bond form. And then the last way we could have made this is by adding in the methyl group. And let's go ahead and draw that. So we could have had another ketone with a carbonyl and an alkyne on there. And so what would be a good we'll use methyl magnesium iodide. I think when you buy solutions of the Grignard reagent with methyl, the iodide is more common. Maybe because methyl iodide is less volatile, whereas bromomethane's a liquid. Or you could use methyl lithium. We have bottles of that in our lab as well. And we work this up with a water workup. And there you go. You got a brand new there's 3 different ways you could have made this same alcohol. And oftentimes when I ask you to do multi-step syntheses on my exams, on my problem sets, you have to work backwards like this. It's like, how do you take benzene and convert it to this? Well, you know how to put an acetyl group on a benzene ring, right? We just spent 2 chapters ago teaching you how to do that. So, there's numerous different ways we could have synthesized this. And when I ask you to do multi-step syntheses, sometimes instead of working forwards, the easiest way is to work backwards. I'm just going to write Friedel-Crafts here because I hope you've been studying for that exam that's coming up on Monday, where I really expect you to have mastered electrophilic aromatic substitution as a way to make bonds. Okay, so we are, let me just check on our time right here. So we're frequently going to be thinking about cases like this, where sometimes we want to be able to do chemistry when there's an OH group on our molecule. And I told you, if I take methyl magnesium iodide or methyl lithium and I treat it with this OH compound here, it will never react with the carbonyl, because before it reacts with the carbonyl, it will first react with the OH compound, the OH group, and protonate our Grignard reagent. And that's not what we want to happen. So we need a trick. What we need a trick is we need some way to protect this OH functional group so it doesn't react with our highly basic and reagent like a Grignard reagent or an alkylithium. So all right, needs protection. How do we protect that OH group so it doesn't react? And I'll show you how we do this. So how is it that we do this reaction? So that our what we need to do is change that into something briefly so that we can then turn it back into an OH. And the protecting group that we almost always use nowadays in organic chemistry is to convert that into a silyl ether. Why do we do that? Because we can do it in 100% yield every time. And I'm going to show you the magical conditions that you simply need to memorize for converting this in 100% yield. What a feel-good reaction into into an oxygen silicon ether. And so here's what that would look like. And initially I'm going to draw this with a trimethylsilyl group on there. You can make those in 100% yield. And the way you would do that is you would react that, and we're not going to talk about the mechanism. You may think you know what the mechanism is. It's not exactly what you think it is. Using TMS chloride in imidazole. Now the problem with this is that once you put a trimethylsilyl group on there and turn it into a trimethylsilyl ether, you've never seen anything like that before. You must be thinking, like, why would they do that? That looks so strange. But the reason why is we can do it in 100% yield and take it off in 100% yield in minutes. The problem with the trimethylsilyl is it's a little bit unstable. So somebody figured out, if instead of using trimethylsilyl, if you use O-tert-butyldimethylsilyl, and that reagent costs pennies, that now it's a stable oxygen silicon bond. You can chromatograph it, you can expose it to water, and that bond stays super stable throughout all of those processes. And it's stable to Grignard reagents, it's stable to alkylithiums, it's stable to all kinds of chemistry. And I'll show you in a second how you get that off of there. So now we can start fiddling around with that carbonyl group. We've generated this silyl ether. And you may think, well, this is kind of complex to draw a silicon with 2 methyls and a T-butyl group on there. Usually we draw that like this. We draw it as the book does it like this. Tert-butyl, that's a italics T there. It's kind of hard to see. Tert-butyl dimethylsilyl chloride. We usually write it out like typewriter style. Let me be a little bit more precise here about what I'm actually writing, because that's not exactly the way it's abbreviated. It's butyl dimethylsilyl, and we usually write italics T hyphen. That's the textbook style. That means tert-butyl dimethylsilyl chloride. So we usually don't draw the structure of the of this silyl-protecting group. Now we can add Grignard reagents, alkylithium reagents, lithium aluminum hydride, anything we want to that carbonyl, and this oxygen-silicon bond will just sit there the whole time and do absolutely nothing. None of these reagents will affect, no matter how basic or nucleophilic, won't affect that oxygen-silicon bond, except for one special set of conditions I'll show you in a second. So now we can add another methyl group to that to that carbonyl, and our group is still sitting here. Now, chemists kind of get tired of drawing out this O-tert-butyldimethylsilyl, so they have an even simpler abbreviation, TBDMS chloride. Wow, all those acronyms. And then when you write this out, they frequently just write TBDMS because it's easier to type that out as you're drawing structures using ChemDraw. And now, how do you get that silicon group off of there? We have a set of magical conditions that you have to memorize. There's no way around that. Here's the conditions. You use tetrabutylammonium fluoride. It's an ammonium ion, but instead of H's on the ammonium ion, you have 4 butyl groups. This is kind of the ammonium ion doesn't associate with the fluoride. It's like using a naked fluoride anion. And silicon loves fluorine bonds. Silicon fluorine bonds. It'll pop that off. Don't worry about where the proton comes from. The book doesn't talk about where the proton comes from. The fluoride knocks off the silicon, and then in the workup you protonate it, and the book never mentions that. Don't worry about it. You just need to write this, tetrabutylammonium fluoride. Let me circle the plus since I circled the minus on fluoride. So putting on T-tert-butyldimethylsilyl protecting groups, it's TBDMS chloride and imidazole. You may have forgotten what is imidazole. You don't need to know what it is. It's the side chain of the amino acid histidine. And it just happens to be the perfect base for this reaction. Man, that's a high yield. Perfect. The reaction gives you 100% yield putting the TBDMS group on, 100% yield getting the TBDMS group off, and that silicon ether isn't affected by powerful nucleophilic or basic conditions.